In this video, I'll be starting our discussion of degenerate perturbation theory. And so this will take this lecture and then two other ones after this to get through. And so degeneracy is when two or more states share the same energy. So the states are then degenerate. And so if that is the case, then these formula here that we got in the previous video won't work, because these two energy states here will be equal, and so we'll have a zero in the denominator, and so that doesn't work, and so we need a degenerate perturbation theory. So a degenerate state, as I said, is one that has multiple independent wave functions giving the same energy, and that will also be true for a linear combination of those states. So adding a perturbation can lift or break the degeneracy by having the energy levels split. To find a linear combination that describes our unperturbed state, we can look at two solutions at the perturbed states that are perturbed by some factor of epsilon here. And you'll probably notice right away that, this is just kind of an exercise in looking at what happens with perturbation and the lifting of degeneracy. Because if we knew the degenerate states, if we knew what the solutions were for the degenerate states, then we wouldn't need this perturbation theory. But what we're going to do as kind of an exercise in this video is assume that we know the solutions for the perturbed states, and then sort of remove that perturbation to see what the solutions are for the unperturbed states when we have the degeneracy. And so we can look at it like this. If we have epsilon here that lifts the degeneracy, then when epsilon is at 0.5 here, we see that our states are all non-degenerate, because the different states will have different energies. Those that degeneracy has been lifted. Whereas if we sort of take this epsilon back to zero here, we end up recapitulating those degeneracies there, where now these two states right here and here now have the same energy right there. And so we'll essentially be doing this. So a particle with mass m in a 2D oscillator has the following potential, or the following Hamiltonian rather. And so we add this perturbation here that is a function of x and y. We have our epsilon here, which is what we will be manipulating. And so this will look like this right here. And so this is in the perturbed state right here. So we end up with this sort of oval shape. And so this is sort of looking down at our function here. And so this would actually be like a bowl. So the function sort of decreases as we go to zero. So this is the sort of bottom of our bowl here, and this line around here would be sort of the rim of our bowl. And so we see that this is sort of an oblong, an oval looking bowl right here that we are looking at when we are using this perturbation right here. And so we're saying that we know this perturbation already, which, as I said, is kind of why this is just sort of an exercise in kind of understanding this degeneracy and the perturbation that comes with it. Because if we already knew this, then we wouldn't need perturbation theory. And so this is perturbed from a sort of ideal, which would be something that looks more like, well, if we remove that perturbation. So it would be something that looks like a circle like this, so sort of a perfectly circular bowl there. And so this S right here is adding our perturbation. So we take that up to the 0.5, and that gives us our perturbation. But you can see here that this is rotated, and so that is something that we will have to do here in a little bit. And so we have our solution for the oscillator from an earlier video, which looks like this, where this thing in red here are the Hermite polynomials. And so we'll be looking at the first and second Hermite polynomials, where this xi here is is just a function of x. So this is a function of x, and we just have this, the mass, the frequency, or the angular frequency, and the Planck constant there in the radical, but it's a function of x, and so you can just kind of think about it as a function of space. So the unperturbed first excited state is doubly degenerate, and one basis for the two states is this psi sub A and psi sub B, where the solutions are this. And so these come from the sort of one-dimensional solutions. And so we have our first order Hermite polynomial and second order Hermite polynomial, which is just a 1, and then this thing here with the y. And so we're doing it in 2 dimensions because so we have a y and we have an x here. But the x, which was just the first Hermite polynomial, is just a 1 here. So if we go through the math here, we end up with this for our first state right here. And if we do the same thing for the second state, so the first state is the one where we have this psi sub 0x and psi sub 1y. The second is when we have the psi sub 1x and psi sub 0y. And so for this one, we end up with this solution right here. And the difference to note is that we have a y here and an x here. And so our Hamiltonian is the sum of the sort of ideal Hamiltonian plus our perturbed Hamiltonian, where this part right here is our ideal Hamiltonian, and then this part here is our perturbed Hamiltonian. So we factor out this m omega squared. Then we want to do this rotation, which I showed before, which makes our solution easier. So we make this substitution. We sort of go through all the math here, which as usual, if you want to look at this yourself and sort of look at it in more detail, the lecture notes will be linked to in the description down below. But what we end up with is this right here. And so we have this 1 plus the sigma, or the epsilon, and the 1 minus the epsilon, which is what I have here. So it's the 1 plus s and 1 minus s right here. And so when we have these two things, these are independent 1D oscillators with exact solutions given by this product here. And so these solutions here are the 1D oscillator states with this frequency, and whose energy eigenvalues for the Hamiltonian we came up with for the ideal plus our perturbed here, where our perturbed energies are given by this and this, and so the energy is just the sum of those two things. And so this gives us our graph as a function of our epsilons. So this is the same graph as above, but now I've put in these solutions here for our wave function. So we have this linear combination because this is the degenerate state, and so over here is when we add the perturbation and we lift that degeneracy, but over here is the degenerate states here. And so we can look at what's going on here. So like I said, this S is our epsilon here, and so we can actually see what happens when we take that to 0 and we get back our degeneracy here. So we go back to our ideal states here, and then if we add that here, we can see that that gives us this rotated oval shape here. And we can see we could have rotated it the other way here, and so I'll link to this calculator here if you want to play with that yourself. I'll link to that in the description down below. All right, and so we have this. So this is on the right side of this graph here. This is where the perturbation has been added, and so the degeneracy is lifted. So the level 1 here is just our energy 0, 0. Up here we have the energy 1, 0 and the energy 0, 1. Then up here is the 0, 2, 1, 1 and 2, 0. And so when we have epsilon equal to 0, we have that the E01 and E10 are equal to each other, and these three are equal to each other. And so we have these degenerate states here. And so when we take our epsilon to 0 for the first excited state, we have these two frequencies here converging down to this single frequency right here. And so from our solutions above, when we put these into the equations here, so we have this x minus y over square root of 2, we can sort of split this x and the minus y, so we have the minus there, we have the y over square root of 2 and the x over square root of 2. And so we just factor out this 1 over square root of 2. But what we see here is now we have these two terms here, but these are the two terms that we had for our solutions above, the psi A and the psi B there. So the solutions we found above, up here. So these two solutions right here. So this was what we found when we were looking at it for the two sort of unperturbed states here, and then we just add those together to get the degeneracy, and so that's what we find right here. So we just end up getting our two states there, and so we know that one of the states is this one, so this psi minus here, and if we do that for the sort of the other subscripts, so here we have the psi sub 0 and psi sub 1. If we do it for the psi sub 1 and psi sub 0, we get the plus version of it here, and so we end up with this for our eigenstates there. But as I said, the problem here in this instance, we knew the eigenstates of our perturbed Hamiltonian here, and then had our perturbation go to 0 as epsilon went to 0. But in real situations, we won't be able to do this, because if we knew what the solutions for our perturbed states were, we wouldn't need perturbation theory. And so this video, I guess, is kind of the motivation for what we need, why we need our degenerate perturbation theory. And so, like I said, the perturbations will lift these degeneracies, which I guess is kind of the other takeaway from this video. But the other one, as I said, is that we do need this degenerate perturbation theory. But anyway, I hope you found this video interesting, and I will see you in the next one.